we start interpreting the functions. Okay, so I'm just going to share my screen. Uh, so we had talked about a number of examples. So let us look at and one of the things. So we stopped with the transcendental function. What is transcendental function, which has uh, sine, cos, and other trigonometric functions. One of the things that we talked about is the composite function. Okay, so let us just look at one example of a composite function. So let's look at this example. You're able to see my screen?
Yes, sir. We are able to see your screen.
Yeah. So let us say that a person is infected with viruses. Okay, measured in trillions. V is the virus. Okay, and the it's the infected value is a function of the degree of immunosuppression that the person has. So if it is 1, okay, then it is turned off, and so it reduces, or it can be, or in other words, it can vary from 0 to 1, right? So let us say that this viruses completely turned off means 1, on means there is, complete there is no immunosuppression, so there is no virus. So let us say that there is a relationship between this immunosuppression and the virus, which is given by 5I squared. Okay, so that is a 5I squared. Okay, then the fever is associated with this infection, and the fever is proportional, okay, to the number of viruses, and the fever in centigrade is given by this equation. Okay, now usually people are familiar with what with Fahrenheit. So centigrade people may not use it, so we have to now convert that Fahrenheit to from centigrade to Fahrenheit as well, and so that is the equation that converts these things. So if you really look at it, there are 3 things in this. One, we have the immunosuppression, let me call that as IS. From there, we go to the virus, the number of viruses. From there, we go to the fever in degree centigrade. Then we go to what is called as the Fahrenheit scale. So what we do is we first calculate V, then calculate centigrade, then calculate the the Fahrenheit. So it looks straightforward, but this is exactly what we meant by a composite function, one acting on the other. So if I write this mathematically, then function of I is the first step, and then I this is with respect to the virus position. Then that is the fever. I act on it. Then I get the centigrade on it. Then I get the Fahrenheit. So you look that one after the other. So which can be written in our earlier thing as FC, fever FE I put, FE, then FV. So that is the composite function. This is just a simple example to understand what these composite functions are. So we had so far seen what are called as algebraic functions. So we had seen algebraic functions. There is so in other words, there were algebraic operations: x squared, x power 1 by 2, and so on. So we had looked at functions based on algebraic equation. Now, there can be functions which are based on trigonometric equation, trigonometric and reverse trigonometric equation, trig and inverse of inverse or inverse trigonometric equations, trigonometric functions. These are called as transcendental functions. Transcendental functions. Okay. In other words, they are based on sine, cos, etc. Right. So before we go further, we can do a number of operations on these functions. So what I'll do is I'll just stop here for a minute. If there are any questions, last class, I think I should have asked it first. If there are any questions, I'll answer it before we go further. Is there any questions?
Last class we were reading about the function and
Yes.
finding the value of the x things.
Yes.
And
Yes.
I read some of the examples like what is domain, what is range, those
Yeah.
things, sir. And if it is equated to any particular sum, it will be useful so that it will be little more clear, sir.
Yeah.
Like
So that is
yes.
why I gave you this example.
Yes, sir. Yes, sir.
Yeah. Okay. So
Yes, sir.
this is the example. So I'm going to show you a number of examples as we go along. So we have only because we have defined everything.
Yes,
Okay.
sir. Yes, sir. Yes.
So this definition. Now we will see this. For example, this is one example of composite function.
Yes, sir.
Okay.
Yes, sir. Yes, sir.
So we will see a very many number of examples. I will also ask you to do it. We will also introduce MATLAB shortly. Okay.
Okay, sir.
And we will see, especially we will take examples from physiology, and we will understand these things. Okay.
Yes. Yes, sir.
So before we go further, there are some operations that are possible with functions. So we'll take see what I'm going to do is I'm going to take functions and then start interpreting them. So that is the most important thing. Functions that you will see that in real life. You can also look at functions. Functions are nothing but equations. Another word at a lower level you call this as equations. But function is a better term because of the more broad term. Okay. So let us say y is equal to a function of x. Okay. So now there are a number of operations you can do on this. I can shift, say, for example, it can be any function. Let's say that the function is like this. I can now shift this graph upwards by, say, 2. Then the new function is equal to, I've shifted it, so fx plus 2. Okay. So I can shift it down. Say 2 is just a normal thing. You can be plus c. 2, it can be 2, it can be 3, it can be 4, and so on. So actually, when I go down, I'm shifting it down. Then that is y is equal to function of x minus 2. I'm shifting it down. Clear? So there are other things also that I can do. That is up and down I have shifted. Now, let me take this function. Okay. And then I'm going to shift them horizontally. Okay. Now I'm going to shift it to the left. So let us say that I'm going to shift it to the left. I'm going to, it may cross it. Actually, I think it's better that let us say that means this point comes here, and then it may be like that and so on. So now I'm shifting it to the left. Then the new function that I get is written as x plus c. So c is the amount that I'm shifting. It can be, say, let's give a value to this. Let's say that it is 0.5. Now let's understand this carefully. What is this? At least the previous ones are easy. I'm just adding one constant here and shifting up and down. So now I'm shifting it to the left. What does this mean? Let x be time. Say, let us say that it is, let's say that it is time. So let us say this is time. T, I'm shifting it to the left. So t plus, say, 0.5. So in the new function, what's happening? Can someone interpret for me? So the interpretation is the key here. The interpretation is the key here. So what is happening at t in the new function, okay, is what had happened at t plus 0.5 in the old function. Okay, t plus 0.5, what had happened at t plus 0.5 is now happening at t. Okay, shifted horizontally to the left. Okay, so, and I can shift it to the right by, how do I do that? So then I shift it to the right. Like that. Okay. And so my new equation is t minus, suppose this is t minus 0.5. Okay. I'm shifting it to the right. Okay. So here what happens is, what happened at this t, okay, is now going to happen at t minus 0.5. That is, before that it would happen. Sorry for the thing. So it will be, so that will be shifted. So what is, so now please understand this. So this is, sorry for this confusion, 1 minute. Let's understand this carefully. So suppose, let's say that I'm going to look at a function. So the original, what is the original equation? Is equal to function of t. Okay. Now, so suppose I'm saying I'm taking t is equal to 2 seconds. Okay. So original, I'll write that in black. Y is equal to a function, that function at 2. Okay. Now, the new one, y, the new, what I've shifted is, what is that?
1.5.
What would, pardon?
1.5.
1.5.
Minus 0.5.
Yeah, minus 0.5. So what do you make out of this?
It has happened, whatever has happened earlier is 0.5 seconds earlier.
Earlier. So 1 point, so t 1.5. I mean 1.5, right? So then you would see that it is actually looks as if it's shifted to the right. Actually, what has happened is it has happened earlier. Okay, earlier. So same way, in this case, it is going to happen later. Understood?
Yes.
So there, t is equal to 2. So we have y is equal to function of 2. Then y is equal to function, new function is 2.5. So it happens later. Okay. Is that clear? So
Yes.
this example would tell you what really happens when you're shifting this graphs. Okay. Uh, Let us now understand what, with these things, let's understand uh, certain other factors before we come back to this shifting. So how do I now interpret an equation? That becomes very important. One of the famous equations that is used, okay, in enzyme uh, mechanics and other things is what is called as Monod growth function. So our right job is looking at the equation or a function, how do I interpret it? Okay, this is for enzyme reaction, and this has resulted in a very famous equation called Michaelis Menten equation or method. Anyone familiar with it? Enzyme kinetics?
I guess it should be the bacterial growth or something like Monod's equation.
Yeah, Monod's equation is, say for example, the equation reads something like this. Okay, so this is the equation. Km is a constant, okay, which is called as Michaelis constant. C is the concentration. Let's see what is this A. Now, the C increases. Let's see. Let us see how this be. Let us plot this graph. So that is C, and that is B. Okay, that's B. Now, the speed of reaction, sometimes called as R, and so on. Now, how would this equation look like? In order to understand it, let us say that the concentration is 0. Then obviously V is equal to 0. If I now substitute 0 here, it will become 0. Now, the next step, I keep on increasing this concentration. Let us, for the time being, assume, just to interpret it, assume Km to be 1. Okay. Now, C takes the value of 1, 2, 3, 4, 5, 6, and so on. Let us say that, let's find out A. What is A? How do I calculate A? So as I keep increasing C becomes bigger and bigger when compared to Km. Understood? The C becomes bigger and bigger. So when C is equal to 5, this equation becomes A into 5 divided by 1 plus 5. When when C is equal to 10, A into 10 divided by 1 into 10, and so on. You notice one thing. Initially, first step, V is equal to A into 1 divided by 1 plus 1. That is A by, first thing. Then I keep on increasing C concentration, then you would notice that A is 100. Suppose A is, I mean, C is 100. Not right. B is equal to A into 100 divided by, okay, 101. You would notice that as C increases, this value and this value are very, very close. And so I can approximate it to A because they're very, very close. So the curve, how would it look like? It would go like that, increase, and then there would be no further increase. Even 200, it will be 200 by 201, which is approximately equal to A. So if this is A, this is a very famous curve, and there are a lot of curves like that. This is how you interpret a function. So as C increases, you would notice that A is approached, never reached. There will always be a small gap between them. A is approached. So A is the saturation point, and A is, full saturation point, but A will never be approached. So is that clear? So the first thing what we have to do is how does the equation behave? Say, for example, when I keep increasing C. So this is the result of that equation. AC divided by Km plus C. Of course, where does this reach very, very close? That depends upon Km value. For another Km value, it can be, we will see that in MATLAB towards the end of the class, it can be like this. For another Km value, it can be like this, and so on. Nevertheless, ultimately, all the guys have to lie very close to this quantity A. They will never reach A. So in mathematics, we call this as an asymptotic value. We call this as horizontal because it's horizontal. We call this as horizontal asymptote. Is that clear? So the interpretation of this equation. That is why you get A like that. Your SpO2 curve is very similar. Okay. So there are many curves, and all these curves are of this function. Clear? Any questions?
Yes, sir.
Yeah. Okay.
Yes.
If there are no more questions, we'll continue with looking at other interesting functions. We're going to just look at other interesting functions, okay, and we will see how they behave. There are interesting cases. Before we go to the transcendental function, let us look at what is called as the power functions. Again, they are very useful. Power functions are of the form x power r. Okay, so function x is equal to x power r. Right. So how does this look like? Before we see the example, let us look at. So on one hand, I have x. On other hand, I have y. That is, let me call that as y. Or function x, that is y. So now I'm going to take various values of r. Okay. Now, if I take r is equal to 0, how would this look like? How would it look like? So this becomes x power 0. What is x power 0? 1. So x power 0 is 1. So this function will be just a straight line. Is that clear? Because you're going to face this kind of functions quite often in all the work. So x power 0 is equal to 1. So I get a straight line. Okay, straight constant line rather, which is 1. Is that clear? Any questions? Hello?
Yes, sir. Clear.
Yeah. So suppose r is equal to 1. Now how do you understand this? You substitute r in that equation. Y is equal to x power 1. What is that? X. So y is equal to x. How will this be? How will this curve be? X is equal to y. How will this be? It will be a straight line like this at 45 degrees. So that whatever x you sorry. So whatever x you take, the same value. So this angle is 45 degrees. We will see that why it's 45 degrees. So it's a straight line. At 45 degrees, if you draw this line, as you move towards x here and go to this point and hit the curve, you would have moved exactly the same distance in this direction. Okay, so x is equal to 1 is a straight line. Sorry, r is equal to 1 is a straight line. Clear?
Yes, sir.
Yes, sir.
Now,
Yes, sir.
Yes, sir. Yes, sir.
now let us say r is equal to 2. So what would be the equation? Y is equal to x squared. Right? So let's see how this equation looks like. How this curve looks like. Very interesting. It will go like this. So this is that curve. It is not necessary that r should only be a whole number. So I can have y is equal to x power 3.5. How will this look like? That'll be very interesting. So this would look like that. So this is 3.5. I said it can only be a real number. So I can also have x power 0.5. How would that look like? Let us see how that looks like. It would look at this carefully. It would look y is equal to x power 0.3. How would this curve look like? I will plot that in MATLAB later so that you are sure. I mean, you can plot it, but let us see how that looks like. That curve looks. So, see the shape of the curve. What is the moral of the story? The shape of the curve depends upon the value to which it is raised. Okay, we call this as a general exponential function. So look at this. Look at 3.5. It raises slowly, but it hits at some point, just goes off. Can someone tell me what is the X value at this point where every fellow meets? Every fellow meets at that point. One. So when x is equal to 1, whatever be the r value, y is equal to 1. 1 power 1 is 1. 1 squared is 1. So all values are 1. So all these curves hit. So what's the important thing? You cannot decide how the curve varies, okay, with time. This can be time. And these curves can represent, say, cell growth rate. So if for example r is 3.5, and let me zoom, r is 3.5, and you are going to only look at this part of the curve, okay, you may say that, oh, it's only slowly raising. But after some time, look at how this is going to raise. We'll quantify it later, but look at that. So in other words, you may not be fooled by the initial values, okay, of a curve. So for example, this curve, if you look at it, okay, it has risen fast, but after some time it slows down. So we have to really understand that equation and how different R's would look like. So mathematical models give you this type of equation, like what we see just now. We just now saw uh, our Michaelis-Menten equation. Like that, you may get an equation x power r. Now, when you get an equation like that and look at the function, you have to be careful that when you interpret, this is how it can be. Right? Is that clear? Any questions? Now, let us say that, okay, why should you put positive r? R can be negative. Okay, r can be negative. So, like for example, y is equal to x power r, where r can be minus half, minus 1, minus 3, and so on. How would this graph look like? X versus y. If I now plot it, obviously, whatever be it, 1, 1 is going to be satisfied. So, that is a curve which is, let me, give me a second. Let me draw it clearly. Okay, so that may be a curve which is, say, x power minus 1. So this may be a curve which is x power minus 3. This may be the curve for x power minus half. Again, you see that the curves can cross over. Okay, so this becomes very important. So what is so are there equations like this? Can someone uh, give me a formula where, what am I writing, x power r? Is there a formula like this? Anyone? there's been study between, yeah, especially in mammals, a connection between height or length versus the body mass. And the equation is 5.3 b power 2.5. Okay, so this may vary. Just one example. So you see this kind of equations in your daily life. Okay, what is a what's a more famous equations which is close to this? Anyone? Doctors? Equation
BMI.
where BMI. Fantastic, fantastic, fantastic. What is BMI?
Height by meter.
M by h
Yeah,
square.
M by height.
Yeah, M by h square. Okay, so that's again where you have h power minus 2, right? So you have equations which are, which have that kind of form. Okay, and you have to, the interpretation becomes very interesting in which case, right? So minus power, saying this, it would be somewhere between the two, between the two. Okay, so now x becomes h, r becomes minus 2, and there's a constant m to it. Okay, any questions? So the that is the interpretation of. There have been changes in BMI definition. Let's not worry about that. Now there is another interesting equation which is similar to this. What's it? So the equation is circulation time, blood circulation time T. So this will be exercises for you. You can, when we introduce MATLAB, you will do these problems. So is A B power 1 by 4, where B is the body mass. So you can see how that equation, okay, zero point 0.4 is somewhere similar to this, similar to that. So circulation time, very interesting, okay, because look at that, the curve, how that yellow curve is. So now x is, what is x? That's the body mass, B. Okay, and that's the circulation time. So after some time, what does it say? Whatever be the body mass, if the body mass increases, okay, the circulation time is not going to increase. That's a very interesting thing. So if I now plot it, it would be something like this. So if the circulation time had been, say, this R, that if that had been, uh, say, 2 or something, then it would have been horrible. You will be somewhere here. Circulation time would increase. So why is this so? So what is that you do in physiology? Now, why is this one by 4? How is that the circulation time is saturating? Why is it that it's saturating? So these are the interesting questions that you would see in research. Right? Any questions? Right. You can work out how much, say, 1.5 times. someone becomes from 70 kg to 100, how would this work? Okay. Now there are other interesting equations. I'm going to list this down and I want you to draw graphs with MATLAB. What is that equation? Heartbeat, H, okay, is 241 p power minus 0.25. Okay, so which is same as before. So the equation is the curve is, look at that, the minus 2.5. So this is um, inverse to what we have here. I think I wrote down, yes, I wrote that down correctly, b power 4, yeah. So that is plus, this becomes minus 0.25. Right? So what happens to, let's say, I mean, you would have done some work, many of you would have looked at mice, for example, uh, especially cardiologists would have looked at mice. So let us see um, what happens in a mice. So generally, what do you know about the heart rate or frequency or heart rate for a mice? It's very high, right? Faster.
Sorry to
So let's see
one
why. Yeah.
so this equation is already derived and it's ready, sir, for heartbeat, to mice, humans, everything same or like?
Yes. Interestingly, it is for all mammals.
Okay.
So let us now substitute and see. 100 grams mice, right? Okay. Now, so let's say what happens in 100 grams. What is the heart rate? 241, 1 divided by 0.1 power 2.25. That is what is called, that is what is this. B is in terms of kg. Please note that's in terms of kg. When I calculate this becomes 428.6. Okay. Let's look at an elephant. So about 5,400 kg elephant. Substitute that. 241 into 5,400 whole power minus 0.25. If you have a calculator, you can calculate. That happens to be 28.1. So 28.1 beats per minute. So how does this graph look like? These are the things, right? We had seen it. So if I now, so it is 1. So how would this look like? So that is the, say, mass. Okay. And this is heartbeat. Then the graph from our previous experience here should be something like this. Clear?
Yes, sir.
Yeah. Oh. Okay, these are some of the questions which I'm going to ask later. We'll come to that. One of the key. Now what is that we have done? We have put, so x power something. So let us look at other functions, exponential functions. The previous ones are power functions, so we go to exponential functions. Okay, so exponential functions are of the form y is equal to a power x. Okay, if it happens to be what is called e, we will come to that in a minute. We call natural exponential functions. Okay, now let us look at this this curve. What is this connection between a and x? So let's say that I'm plotting x here and I'm plotting y here. Okay, so I'm going to do that for various values of a. For various values of a. So do you think all the values, like for example, I'm going to take a is equal to 5, 2, a is equal to 0.1, 0.5, whatever it is. Do you think it will all cut at some place? So this is minus. This is minus x, this region. Do you think it will cut at some place? What happens at x is equal to 0? So a power 0.
A power 0 is 1.
1. So at the 0, there should be y 1. Right? So that is 1. Yeah. So all my graphs have to pass through this. Now let's look at these graphs. So, sorry. So that is, for example, 1 by 10 power x. This is 1 by 2 power x. This is 5 power x. Okay, and same way, this y is equal to 3 power x, and so on. So you would notice that there's a clear, depending upon a, there is a clear difference in its behavior. When a is less than 1, it's going to drop high value to low value. So high value to low value. And when a is greater than 1, from a low value, it is going to increase to high value. Is that clear? You can draw it yourself and you can see it. Right. So we will also see this is exponent. X is the exponent. That's why it's called exponential functions. Okay. So there are some rules for the exponents. Let us just write down the rules. You may know it, but doesn't matter. We will just write down these rules. So I have one a power x, one function, another function a power y. Then if I have composite function, then a, multiplied by a power x, it becomes a power x plus y. A power x, when I raise it to y, it becomes a power xy. A power minus x is nothing but 1 by a power x. Same way, a power y by a power x is equal to a power y into a power minus x. So that is equal to a power y minus x. Of course, we saw this a power 1 is equal to a power 0 is equal to 1. So these are very, uh, very early, I mean, 7th standard algebra. Anyway, we just wanted to refresh it. There are very interesting numbers. There are very interesting numbers in nature. Pi is one of those numbers. Another interesting number is called as E, with a value of 2.71828. E is a very interesting number and participates in so many functions. So there are many physiological conditions which behave as e power x or e power t time. X is something common. I mean, x can be t, so e power t. This is a very, we'll see a number of examples. Okay, so this graph, first we'll draw the graph and then first interpret that. So this is y and this is x. So x is equal to 0. What would be the value of y? 1. Right? So if y is equal to, if x is positive, it will be like this. We call this as exponentially increasing. When x is negative, it will be like this, exponentially decreasing. So y is equal to e power x, y is equal to e power minus x. So these are two interesting things. So all that minuses will be in the left. So it can be, say, for example, for minus 0.1, it can be like that. 0.05, it can be like that. Then that is minus 0.05. Then for other values, say y is equal to 1.7 can be like this, y is equal to 0.4 can be like this, and so on. So moral of the story is, this is a very important equation. If x is minus, it will reduce like this. If x is plus, it's going to increase. So we call this as exponentially increasing when x is plus, exponentially decreasing when, okay, it is minus. Clear? Many times that equation is written like this, c e power alpha x. So that is the general equation. And this forms the basis for logarithms. Okay. And let's look at some example. Let me check. So can someone think of an example of exponent of an exponential function? Anyone? Most of the drugs that, I mean, the drug absorptions and its life inside the body is are all exponential functions. They are all exponential functions. So the let me get an equation. 1 minute, I've written it down. So, for example, yeah. For example, typical equations. Yeah, typical equations are the or mt is some 240 e power minus 2.3 t. So this is a typical equation for drug presence with respect to time. So one of our interest in these kind of equations, many people write this as in pharma, they write this as S of t is equal to S naught, which is the initial dosage, okay, into e power alpha t. This is how they would write, okay. Uh, the equations are written like this. So one of the suppose it is, I mean this equation can be for a drug, or this equation can be for some virus uh, growing with time, and so on. So there are a number of examples which can be given here. So let us take this example. T is say uh, measured in seconds. Okay, what you're giving. So now, one of what is your interest? Your interest is what is called as half life. At what time is the initial value, initial bolus that I give reduces to half? Okay. In other words, let us say that the half life is given as T of H. Clear? So is that clear? So in other words, S of T of H, okay, is equal to 0.5 times S of S, that is initial S naught result. S naught. Right? So this is our interest. So generally we will take alpha and substitute this. So when does this become half of the initial value? How do I do this? I will substitute this in this expression. For ST would be the case. So 0.5 S naught is equal to S naught e power alpha t. Right? So I will cancel S naught out. So e power alpha. Now it's half. That's why I put here. So TH I will put. Alpha TH is equal to 0.5. Right? So in other words, e power alpha TH is equal to 0.5. So we introduced at this stage what is called as natural logarithm, which we will write as ln. Are you familiar with logarithms? Yeah? Yes or no?
After 10th, no.
After 10, no. So you know what is logarithm, logarithmic
Yeah.
functions. Okay. So I'll can I dig your memory, or we will just push that? Okay. So now there are logarithms are written as it's here log with a base which is written here. For example, it can be logarithm with base e, which is usually written as ln. Okay. So for example, I have an equation of the form y is equal to e power x. Y is equal to e power x. What is actually logarithm? Let's understand this carefully. Logarithm is nothing but a function. So what is this function? Let us say that I have a domain, which is R. Now I'm using a function from this domain, which is a function called e power x. This e can vary, it can be anything. Then now I go to a range. Okay, range can be some, say, for example, 0 to infinity. Then we know that this is the forward motion. We know that I want to go back, okay, which is the inverse. So that inverse part or inverse function is ln of x. So how do you define it with this y is equal to e power x? So x, so what is this inverse function? What is a forward function? Given x, I can get y. That's what this means. What is the inverse function? Given y, how do I get x? So that is where my logarithm helps me. So given y, if I apply this logarithmic function, I will get x. From where did I come? I came from e power x. Fortunately for us, this function is well documented. I need not worry about it. There is a function exists, which is called as a logarithmic function, okay? And then I can do an inverse. Suppose instead of e power x, I put 10 power x. I'm going from 10 power x. Then I have logarithmic function to the base 10, okay, is what I will use to go back. So, no, not x here, ln is what go back. So in other words, I will get x is equal to log to the base 10 y. It is something like this, x will come and sit between the two, so that 10 power x is equal to y. I can go back to x is equal to log y. Clear? So it is just nothing but an inverse function which helps me to go back. Because of the fact that I had the previous things I had written down, a power x into a power y is equal to a power x plus y and so on. Similarly, I can show that logarithm also has some rules. Log of two numbers multiplied x and y is equal to log of x plus log of y. Log of x power p is equal to p log of x. Log of 1 by x is equal to minus log of x. Log of x by y is equal to log of x minus log of y. Log of e to the base e is equal to 1. Obviously, this is going to sit in the middle, 1. And log of 1 is equal to 0. So because e power 0 is equal to 1, that's going to sit in the middle. So e power 0, and that's equal to 1. We can prove each one of them. That's not our job now, but these are some of the logarithmic functions that you would use. So if I now write log of 3 power 4, I will use this guy to write 4 log of 3. Logarithms are very, very useful to us. We will see how we are going to convert some of them to our advantage. Right? So let's get back to our doubling time. Fortunately, we know these values, it's available in calculators, it's available as a table, and all these things. So e power alpha th is equal to 0.5. So alpha th is equal to, so I'm going to take log on both sides. I can take log on both sides. So when I take log of both sides, log of e to the base e power alpha th, okay, is equal to log of 0.5. I can take log of both sides. Please note that I can apply the same function to both sides. So e power, so what is this? I'm going to use this formula. So that is alpha, okay, th, not ht, sorry. Alpha th. So alpha th now becomes alpha th into log e to the base e is equal to log of 0.5. When I put ln, it obviously means that base is e. So this is, what is this? This is 1. We just now saw this here. So alpha th is equal to ln of 0.5. And so happens that I know there's the value of 0.5. Okay, it happens to be minus 0.6931. So th is equal to divided by alpha. So this is the general formula for half-life. So most drugs follow this exponential pattern. Half-life, you have to find out, you have to know that alpha value, then you can find out the half-life. For example, if the drug is ST is equal to, the initial bolus is 240, e power minus 2.3. May not be the correct example, just took somewhere from somewhere. So alpha is now equal to minus 2.3. So TH is equal to minus 0.6931 divided by minus 2.3. So is equal to 0.3013. So you can also have, see, this is minus means it's coming down. So you can have doubling time. How do you get doubling time? Instead of 0.5, I have to use 2. So, which means that e power, so I'll not write down all the steps, they are here. So I'm going to write down this alone. So alpha th becomes ln of 2. Interestingly, ln of 2 is 0.6931. It has to be so because of this particular, that particular equation. So we have, let me call that as doubling time, TD. So TD is equal to 0.6931 divided by alpha. Okay, so that is the exponential form becomes important, and the exponential, how that can be used, right? So this is very important. This is very important. So now, if you really look at, say, let's put a very interesting case. Let's say that initial amount is m0. So at time t, this is time. 0. Amount left in the body is, say, amount is S0. So, so in a percentage wise, is 100%. Okay. So at half-life, first half-life, we'll call it. It is 0.5. Okay. S naught. So which is 50%. Then from here, I go to second half-life. What is the second half-life? Note this carefully. 0.5 multiplied by another 0.5. So 0.5 squared, which is 25%. Third half-life. From here, we go back again. So this will become 0.5 cubed S naught, which would be 12.5. So we'll do some problems on this. So like this, you can go. So say, for example, 6, if I come, 0.5 to the power 6, sixth half-life, sorry, S0. Why am I doing right here? S0. So it becomes 1.5625. So this is very important to understand. The logarithmic functions and the exponential functions are very useful to you. Okay, and it is. Let's do a.
Can we substitute this S0 for 1 because they're taking it as 100%?
Yeah, you can do that. Absolutely, 100%. You can say that it is 1, and then you can calculate. Absolutely. So you will know when it goes. That's all. Right. So that is not a problem at all. That's absolutely correct. So there are a number of examples. For example, the cancer cell growths. Okay, they are the many of them are exponential functions, and you see the doubling periods there. Okay, doubling period of growth, and so on. So I think I will stop a bit. I will ask Srinivasan.
Yes, sir.
So I'll just stop now. And
Yes, sir.
how many of you have downloaded MATLAB?
I have.
Oh, very good. Excellent.
I have.
Dr. Sundar, Dr. Anson is there?
Yes,
I
sir.
think so. I saw.
Yes, sir. I don't have laptop. Hello.
So, yeah.
Am I audible, sir?
Yeah, please.
Yes, sir. You're audible, sir.
Yeah. Sir, I have not done it, sir. I will.
Yeah, please.
For the time being, we can use online MATLAB online, sir. If you, I hope you have got your Smail ID and you've registered with MATLAB.
Yeah.
No, sir, not yet.
Guys. So please,
All right.
please do that, because we are going to see a quick 5 minutes introduction to MATLAB.
Okay, sir.
Okay, I've stopped it. Srinivasan, just show the MATLAB and just different functions. So I have some MATLAB examples. Before that, we will take some small examples and show. Just explain this thing and what is a script file and so on.
Yes, sir. Yes, sir. So what I'll do is I'll just share my screen. So we can, like I told, for those of you who have not downloaded MATLAB, what you can do is you can go to MathWorks website, you can sign in, and then you have got MATLAB online. So you can go and use that also. I have opened the MATLAB online and we have got this. Alternately, if you have installed MATLAB, then you can directly start working on that. So just to explain the fundamentals of MATLAB, what we see here is what is known as the command window. So various commands that we desire to execute can be directly given in this command window, and it will execute it as and when we we press enter. And the variables that are created, the type, their size, and their values, etc., are usually stored in MATLAB in what is known as the workspace. You can expand the workspace that you find on your left bottom, and you will find the various variables that are declared on the left. In addition to this, what we can also do is in MATLAB is you can write codes and then you can compile it and execute it once for all. So I hope my MATLAB screen is visible. So in your home screen, you will see what is known as the editor, right? In this editor, you can create a new script file, and the script file will be having a compendium of various commands that you would like to execute one after the other. Now, let me say, for example, I have got a script that I have written for some work of mine. So whenever I put this percentage, it just means that I'm going to write a comment of it, and MATLAB processor is not going to execute that particular line. So I have just explained what I wanted to do in this using this code in 2 lines. And then I have given various variables name in these lines, and then search and append as a command that this is executing. And then I have written a loop with the details of this loop and other things we will go as we go further on in this class. And then once I type a code like this and I say run, what MATLAB does is just say change folder. It goes to the folder in which I have loaded this code, and it starts executing line by line of what I have written in that particular code. And then I start, I have asked to MATLAB to plot the various curves for me. As a result of which, MATLAB starts auto-generating the curves that I wanted to do. This is just a sample of, just to give a flavor of working in MATLAB. How do we generate these curves? How do we work with all these data? We will be seeing, you know, as we go ahead in this class. So right for now, what I'll do is I will just execute some simple commands and show. Right. As I told, my MATLAB screen has the space that is known as command window. Command window is the place where I execute my commands as and when I type it and I press a word enter. Let me say, for example, I'm going to y is a function of x, and I'm just going to, make, I want a plot for y is equal to x square. Let us say a power function y is equal to x square. So what I will do is I will just say x is linear space of, I want x to vary from 0 to 10, and I just want it to vary from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So totally 11 elements will be there in this, what is known as the array or vector. So I will say linspace. Linspace means linearly spaced from first digit is 0, final digit is 10, and totally 11 entries should be there in between. So I say x is linspace of 0 to 10. So immediately once I press enter, what you see on the right is in the workspace, the variable by name is x is created, and the value is also given 1 into 11 double. And if I double click this, I'll be able to see the values for x written also. So it starts from 0 and goes all up to 10.
Yeah, Srinivasan,
Right?
1 minute. 1 minute.
Yes, sir. Yes,
Yeah.
sir.
So I'll just take over.
Please, sir.
Whatever we have done, a few examples I will show.
Yes, sir.
Okay. I
Yes.
sharing my screen.
Yes, sir.
1 minute. I'll take a minute.
Sir, I'm not seeing any screen.
Yeah. I think there was a problem. Now I share screen. I think there is an issue with my screen. 100. It is share screen, desktop, share window. Are you able to see my screen? No?
Not yet, sir.
I don't know why it is not. Now, are you able to see?
Not yet, sir.
Okay, Srinivasan, you finish it. I mean, it's time. I'll do that in the next thing. With this, I'm not able to get the screen. I'll start next time by sharing the screen. I shifted from one to the other. I think there is a problem. I'll do that in the next class.
Right.
Okay.
Right.
I will share screen. I don't know why it's not coming up.
Sir, maybe did you share window, sir?
I tried both. I shared window. Allow share. Window I'm sharing.
Yes, sir.
It's not coming up.
Yes, sir. Yes, sir. It is yet to come up.
Yeah. Okay. So what I'll do is, I'm sorry about it. We'll do that in the next class. Whatever I have done now, it's anyway time, and I will show you all those as examples. Okay, in MATLAB, so that I'll introduce you to the programming based on the functions that we have seen. Okay, so we'll stop here and we'll continue this next Monday. I'll give a few assignments so that you can just try it out. Okay.
Lecture video will be uploaded tomorrow morning and it will be shared in the WhatsApp group, like what we did last time. And I hope everyone was able to access the last lecture video also. There wasn't any problem in accessing that.
I able to access, sir. No problem.
Yes.
No
Thank you.
problems.
Yes. No problem.
Thank you. Thank you.
Thank you very much.
Thank you.
Thank you.
Thank you all. Thank you.
Thank you.
Thank you.
Thank you,
Good
sir.
night.
Thank you.